Right. So just to remind us, last time I finished with the statement that if you have a finitely generated group which has some finite images, which include, for example, all simple groups, all groups SL2 over infinitely many primes, then actually gamma has many other finite images, in particular.
Onto?
Yeah, onto. Yeah. Then actually exists a finite index subgroup of gamma such that among its finite images we have all the congruence images of the S integral points of some Q-simple simply connected algebraic group. Yeah, and a bit later I'll also mention why this thing has a lot of congruence images. Yeah, so there's a very good description of the congruence images here. Yeah. Okay. Right. The first thing I want to say is that actually here, of course, 2 is not essential. We can replace 2 with any n. And in fact, I think I put n. In my statement, I had to fix n. Right? Yeah. Now I look it back. Yes. But you may think maybe I can also now try to vary n as well and get bigger and bigger n's. Yeah, and deduce some that in addition to these images there are others, but actually it's not true. So if you allow the dimension to increase, here's a result that given a sequence of integers ni, which tends to infinity. In other words, for any escapes from any finite set, yeah, there could be repetitions, but only finitely many repetitions for any given integer. Then and primes pi. Now I don't need even to say that the pi tend to infinity. They could be the same prime if I like. Then exists a finitely generated group gamma whose only finite images, whose finite images are exactly SL ni pi. Well, let me just, I want them to be simple, so let's just take the modular scalars. And of course, if you have these as finite images, you also have their Cartesian product and their products and their finite products.
So just to make sure, when you write SLN pi, you mean SLN of field with pi elements, and ZS is the localization, right? Just to make sure.
ZS is a localization.
Localization, and the upper one is SLN over
FPI,
pi
yeah,
elements.
FPI, yeah. Another way to say this is that the profinite completion of gamma is exactly the Cartesian product of all these SL, PSL, and PI. Yeah. In fact, here instead of primes, I can take finite fields, yeah, and finite fields. It's probably just makes it clear. Then really, I also allow like extensions of. Yeah.
So why does this doesn't contradict the theorem?
Because the degrees,
okay.
The degrees tend to infinity. Somehow, if you have increasing degree, you have a lot of room, and then yeah. Okay. So this is a separate theorem that I proved with Martin Kasabov. And in fact, you can replace this with any collection of finite simple groups whose rank tends to infinity. For example, you can have here the alternating groups, one for each. You also can actually allow even repetitions, but then you have to, yeah. Right. Yes. Actually, here I have to be a bit more careful, because I'm already allowing repetitions with this definition. You know, if you repeat too many, then actually this thing may not be finitely generated. So one of the conditions is that provided this Cartesian product is finitely generated topologically, in other words, there are not too many repetitions of the same group.
So you bound the number of repetitions you allow?
It doesn't have to be bounded. It should be bounded by some kind of function on the size of the group very explicitly. Yeah. But if they suppose they're distinct integers, then there's no problem with that. It's 2 generated in that case. Right. So let's see how to. So obviously, then the fact that these are the same matters, and this leads to the my first step to prove this is to replace gamma with an image which is a linear group. Yeah, to turn out that actually gamma has an infinite linear image, which is not going to be solvable. Yeah? Right. Step 1. Replace gamma with a linear group. Okay. And this is the point when we have all these linearity criteria. And since yesterday we saw a geometric proof of Selberg's lemma, I decided that, and this will be mentioned so many times in these talks, I decided to give you a proof. I mean, of course, many of you know the proof, but I'll give it anyway for those of you who don't. And anyway, it leads to these linearity criteria. So this talk will be today mostly will be commutative algebra. So you're going to see the use of commutative algebra. Right. So lemma. Now we start with the linear group. Let gamma be finitely generated subgroup of GL and F for some field F. Then first statement is that gamma is residually finite. And the second statement is that if the characteristic of the field is 0, then gamma is virtually torsion free. So the virtual always means there exists a finite index subgroup with the property. Yeah? So there exists a finite index subgroup of gamma which is torsion free. Okay. So here's the proof. It's a beautiful proof. Because gamma is finitely generated, if you look at the generators, the generating matrices, we can take all the entries of the generating matrices and just take the subring that they generate inside F. So we can assume that gamma is actually inside as GLN R, where R is a finitely generated subring of K, of F. Okay? And now in a good shape, because now we can basically use congruence images. You know, here we couldn't because F does not have any images. But a finitely generated ring always has many images. So R is Noetherian. First thing. The second thing is R has no zero divisors. In particular, R has no nilpotent elements. Oh, okay, it's a domain. Sorry. the Noetherian domain. Yes, no, because it's subunit for ring. And then there's a property which is called Jacobson ring. This in our situation, the only thing we're going to use is that 0 is equal to the Jacobson radical, which is the intersection of all maximal ideals of the ring. Yeah. So it's known that in general all finitely generated rings over all finitely generated rings over the integers are Jacobson rings. So here in general, if it's not a domain, here you have to put the new radical, the set of all new potent elements. But then now this is what we want, because and also R mod M is a field which is a finite extension, is a finite field. Okay. This is because of the basically weak Nullstellensatz. So the weak Nullstellensatz says that if you have a field extension which is finitely generated as an algebra over its ground field, then actually it's a finite field extension. Yeah. So this one is therefore it's a finite field extension of its over FP. Yeah. It cannot have characteristic 0. And then that's the work. Yeah, because then of course gamma maps onto gamma is residually GL and R mod M. So it's residually finite. Now, for the second step, there's an extra contribution. Now assume the characteristic is 0, but this means that Z is inside my. I can assume that because I'm in characteristic 0, I can throw the identity to my ring, so I can assume that Z is inside R. And then I take two different primes, and I take the prime ideal of Z, and then extend it, find a maximal ideal which contains it. So basically I take PR and extend it to a maximal ideal, call it MP, which is a maximal ideal of R. And I do the same thing for Q. Right? Okay, and now another property of Noetherian rings, which are domains, is that the intersection of all powers of a maximal ideal is 0. And similarly, of course, for Q. And also, because R mod P has characteristic P, so R mod MP has characteristic P. That's the same. The same is true if I take any power. So this thing is a power of P. Okay. It's easy to that's easy to see just from here. But then I take two subgroups, gamma P in gamma, which is the kernel of the induced map of gamma on the projections onto just taking the projection mod MP, and the same thing with gamma Q. Right. And then we see that gamma P is residually finite P group. Okay. This is because if I take GL N R mod MP to the n, and then take the first congruent subgroup. So here, if I take the matrices which are congruent to the identity modulo MP, and they are with coefficients modulo MP to the n, this is a finite P group. Yeah. Yeah, so, and since gamma P is residually here, it's a residually finite P group. Similarly, gamma Q is a residually Q group. But then the claim is that the intersection, yeah, then
so it's not the same n, right?
Ah, yes, it's not the same n. Yes, this is not. This is some k tending to infinity. Yeah, yeah, that's right. So k is going to tend to infinity. I mean, I'm going to take all these intersections, and then because the intersection is trivial, the group is residually in that. Every non-zero matrix will be seen in some of these groups here. Okay. But now, if I take an element here, G of finite order of G, if it's finite, then mass divide is both the power of P and the power of Q. Right, because projecting it deep enough into this sequence for quotients here, we see that it lives in finite P groups, so the order must be a power of P. Similarly, the order must be a power of Q, but then because P and Q are different primes, G is the identity. Yeah, so this group is torsion free. Right? And it's finite index because both of them is finite index. Okay, so that proves the Selberg's lemma. So now I'm going to prove a very useful linearity condition. So great. So I denote by L and P the class of linear groups. The class of linear groups. The class of subgroups of sum of GL and F for all possible F of characteristic P. Yeah, where P is prime or 0. Yeah, so this. And by fine underneath, I mean the class of all subgroups, the class of all subgroups of GLN over finite fields of characteristic P. Yeah? And this only makes sense if P is not 0. Okay. So now let gamma be a finitely generated group. With first thing is that if gamma is residually in L and P, then gamma is in L, M, and P for some M. Right, so maybe it's not linear in the same degree, but it's still a multiple of the degree will do. Yeah? And it's in the same characteristic. Yeah. So if it's linear characteristic 0, then it's linear characteristic 0 if PP. The second part is more interesting. Suppose that okay, now to state it correctly, let me just say that I have a collection of normal subgroups of gamma. with trivial intersection, and such that each quotient is a finite linear group, so it's inside L n pi finite. So each quotient is inside GL n over a finite field of characteristic pi, and pi tend to infinity. Okay.
So maybe I missed, but on the left board you defined LNP field.
Yep.
But maybe you didn't define LNP without fin.
Without fin is just this.
Okay.
Fin means a finite subgroup. Yeah. So now, I mean, here I'm also allowing infinite quotients basically, but here in this statement now, my group is residually linear in characteristics which are all not allowed to repeat more than finitely many times, and each image is finite. Okay. Then, sorry, this is gamma. Then, well, gamma is linear in characteristic 0. So this is perhaps the surprising part, which somehow you start with many different finite fields, and the fact that the characteristic increase somehow allow you to approximate group by linear group. And this is somehow general philosophy that also occurs in many other places. Something you have a statement that you expect it's true in it's true in characteristic 0, and you expect probably if for big enough primes you can actually prove it also for big enough primes. Yeah, this is what happens with Norris theorem, for example. I mean, this is just vague philosophy.
Means the second part of your linearity condition and the aim that you had. It looks very close, right? You had at the beginning, you described an aim at the beginning of the lecture.
Yes.
And you have this second part of the linearity condition. They seem very close.
No, this is just a linear group. I mean, it doesn't say yet about what images it has, but it will be close. I mean, after that, we're going to take the risky closure. The moment we get a linear group, we're going to start to apply algebraic groups. Yeah. But okay, so I want to prove this because this is a condition that appears, I think, in this form is due to John Wilson, but there are many different proofs, also by Dan Siegel, Lubotsky, Mann. It can be traced back to the idea of Maltsev. Maltsev proved something similar, but for groups which are fully residually in this class. In other words, for example, here, if you assume that these Ni's form a chain, if they are ordered by inclusion, then the proof is much easier. Okay, because then basically the group is fully residually in this class. You can take an ultra filter and like use model T. But here, all right. Okay, so enough. Let me just give you the proof. Right. Let's first prove this because it's easier. So what do we have? We have each gamma, right, has a normal subgroup Ni with so we have a collection of normal subgroups with trivial intersection, and they see each Ni sees a linear group. So this we are living inside GLN over some Fi, where each Fi has characteristic P. Each I, yeah, this is the first case. Okay, but then let's do the obvious thing. We embed gamma inside the Cartesian product of all its images by these Ni's. Each one we embed inside GL and Fi. And now a Cartesian product of GLNs, the same N for different fields, this is the same as the GLN, one GLN, but over a ring which is just the Cartesian product of all these fields. Yeah, okay. if you want, this is the moment we're using that we have the same n all the time. Yeah. Okay. Now this is a huge field. I mean, this is a Cartesian product. But after all, our group here is finitely generated. So by doing the same thing, I can assume that my gamma now lives inside GLNR, where R is some finitely generated subring of this Cartesian product. Finitely generated subring. Okay. And right. Well, we are almost done. Now this is a Noetherian. So Noetherian. And here is the important thing. Now we have zero divisors. I mean, this does not sit into any. This does not sit in a field. It has too many zero divisors. Yes, but it doesn't have nilpotent elements except zero. Yeah, Cartesian product of fields has no nilpotent elements. So R has no nilpotent elements. So the new radical of R is zero. And now a basic result about Noetherian rings is that a Noetherian ring has only finitely many minimal prime ideals. So let P1, P2, Pm be the minimal primes of R. Okay? Now, this is a very much simpler statement than the Wittgenstein's that we used, all these results about Jacobson radicals that I used for Selberg's lemma, that they're deeper. This is a consequence of being Noetherian. The proof is several lines, but if you don't know it and you want to know, ask me after the lecture. Now, okay. And then you can see what we're going to do. We're going to intersect them. So now the ring, right? So now GLNR embeds inside now a finite product I from 1 to m of GLNRPI, and gamma sits there. Now each of this is a domain of the same characteristic. So it sits in a field of characteristic P by its field of fractions. And if you have finitely many fields of the same characteristic, you can put them into one field. Yeah. So all of this. And if you have several copies of GLN, you can keep them in block matrices and make M copy. This you can put in GLNM over some field K, where this K contains all R mod Pi. And that's the proof.
Wait, don't you use the statement about the real radical?
Yeah, so okay. That's because the intersection of P1 intersecting P2 intersecting Pm, because these are the minimal primes, this is the same as the intersection of all primes, which by the basic result is the new radical of the ring, which is 0. Yeah, so thanks you.
And what do you use to get the first map to the
I need that this map is injective, right? Because I need the ring embeds in its quotients. Yeah.
Why the others the same characteristic?
Hmm?
Why all the R mod PIs have the same characteristic?
Well, okay. So if you now if you have finite characteristic, the quotient of a ring has the same characteristic. Yeah. And if you have characteristic 0, you can just take them over. You cannot Q to the. So if these were of characteristic 0, then I can, without loss of generality, I can assume that R is a Q algebra. And the moment you have Q, then it survives in any quotient. Yeah. Right. So what's the problem here? Now, if you change the characteristics all the time, of course, if you do this, I mean, you can do exactly the same thing. The problem is that suddenly here, these will not be the same characteristic, and you cannot put them into the same field. So we need to be a bit more careful. So let's now return to the proof. Now, the characteristic, in fact, this is a finite field. It's finite of characteristic pi. Still, we have the minimal primes. Right, where is this? Okay. But now here is my claim. So the claim is that now R, if I intersect it with the direct sum of the fields, these are now just the finite combinations of the finite tuples, the tuples in which almost all coordinates are 0. This is basically a torsion subgroup. This is a torsion subgroup of the additive group of the field, of the ring. Yeah? Yeah, because this is a torsion subgroup inside the Cartesian product. Because now I'm using the primes to go to infinity. Yeah. So if you have something that is non-zero in infinitely many positions, it will have order. It will not have finite order as an additive group. Yeah. So okay, the claim is this is finite.
So what's R now?
R is the same thing. Yeah. And now this is why is this finite? Well, because again, it's true. I mean, so R again embeds into the Cartesian product of R these R mod pi's, right? But then if I take an element little r of a finite order for the L, so in other words, L times R is 0.
This intersection is fine. They are included in the intersection between 1 and 3.
Yeah, it's finite. The claim is that this is finite.
And now we see.
Is that?
No,
Below of that, the intersection of R mod pi.
Ah, yes, you're right. Yes, thank you. Yeah. But then if you have an element of finite order, then because it becomes an element of finite order here, and if this has characteristic 0, it has no elements of finite order. If it has characteristic qi, so let qi be the characteristic of R mod pi. Let this be a prime qi. Any domain has a characteristic. It's the characteristic of its field.
They all have characteristic P. I'm confused. In the last board, you said that R mod pi is a domain of characteristic P where P is.
This is part 1. Here we are proving part 2. So part 2 is now when we cannot deduce that these have the same characteristic. Yeah. Because now we have this situation, and we have that pi tends to infinity. Right? So we have now, these are all finite fields, but they get bigger and bigger characteristic.
So part 1 is they all have the same characteristic? Sorry, can you repeat what did we do in the last part?
Okay, in the last part we have a group which we have this situation. Right, we have this situation exactly as described here, and the aim is to prove that gamma is a linear group in characteristic 0. Yeah. So somehow from these finite characteristics we want to get something of 0 characteristic. Yeah. Right. So the first step, in fact the main step, is to prove that the torsion subgroup of I is finite. Because if I take an element of a torsion element additively whose order is L, then it lives somewhere in this finite product. But then because the characteristic of this is the definition of Qi, the characteristic of this, then L divides the product of the Q1, Qm, those of two which are finite. Yeah. Divides the product of the finite limit of the finite of the non-zero, sort of the non-zero elements Q1, Q2, Qm. Yeah.
So QIs are non-zero.
Some of them are.
Yeah. Yes. Okay. But then these now involve only finitely many primes. So here, actually, this proves that my R actually lives not in the infinite product, but actually here I can put some bound on it, yeah, because it cannot have component which is in a very big field, in big characteristic, because then its order will involve this very big prime, yeah, which is precluded by these finitely many, yeah. Right. So if this is finite,
how you know that there is at least one QI which is non-zero?
Hmm?
I mean, there is at least one QI which is non-zero.
No, but otherwise it's not a torsion.
it doesn't matter. If all of them are zero, then this is torsion free. It doesn't matter. Yeah. Yeah. So so this is finite. But then if it's finite, then we can just kind of project onto it and take the kernel, and that has the effect of replace. Now, basically, I'm saying replace gamma with a finite index subgroup. Gamma 1, and replace R with its intersection with sufficiently big fields such that it becomes torsion free, and get the same well, the new R to be torsion free. No elements of finite order. Okay, but then with 1, because our ring has struggling. But now we're going to force it to have ideals of only of characteristic 0 by the simple trick of localizing. If it's torsion free, then it contains the integers, right? But then we just localize at the non-zero integers. Yeah. Formally, right, this is the localization, which also works for things which are not domains. It's no problem. When you do localization, you have to be careful. So the ring still is going to survive inside its localization. Because we are identifying pairs of ring elements and integers. So I'm thinking of this should be equal to R2 and 2. We're talking about equivalence classes of pair of ring element and a non-zero integer, and this is equal whenever, this is the equivalence relation, says whenever n2 R1 is equal to n1 R2. Yeah, just as if you're building the field of fractions. Yeah. But then in this, what is the bad thing can happen? Maybe some R1 can become equal to 0, right? But for this to happen, there must be an integer such that nr1 is basically 0. So only torsion elements will be killed by this localization, but they are not torsion elements. So R lives it in field of fractions. Yeah. In some ways, this is the same way you take a torsion-free abelian groups and think of it as a vector space over Q. Yeah. Yeah. Right. But now in this new ring, this is a Q algebra. This contains, we force it to contain Q, and then we just do the same thing. Now we take this one has finitely many. It also has no nilpotent elements. We just inverted some of the elements of the integers, but we have not created any nilpotent elements in the process. So again, so R again this R prime. R prime has finitely many, so has minimal primes, minimal. prime ideals P1, P2, PMC. These are now the new primes for this ring, yeah? But again, the intersection of them is 0, and now the characteristic of each R mod Pi is 0. Because they're vector space over Q, yeah? So you're just forcing them. And then we're done, yeah? But the same argument. Now this became O of characteristic 0, and then case of characteristic 0, and instead of gamma, here I have gamma 1. But if a finite index subgroup is linear of characteristic 0, then we can just induce the representation and get yeah. Oh. Sorry, this took too long. Right, okay, so this is good. Right, so now, okay, so now here, therefore, I can, because, now let's return to the, now let's start, now we are back in the world of linear groups. Right, so now let's return here. What we have is that my gamma has some subgroup of index, some normal finite index subgroups, such that gamma mod Ni is isomorphic to some linear group, yeah, SLN FPI, where Pi tends to infinity. Well, these may not intersect trivially, but never mind. Just consider gamma bar, gamma modulo the intersection of all the Ni's, right? And then apply the linearity criterion. Apply linearity criterion, and get that basically L gamma bar is a linear group in characteristic 0. So it lives inside GL capital N C in characteristic 0. So okay, right? Because we are only interested in the finite images of quotients, then I can replace in the whole theorem. I can just replace gamma by any quotient that I like, provided I can prove it for the quotient. Right. Okay. And notice that this group is not virtually solvable. Why? Because it still remembers these subgroups, these quotients, and these quotients are not virtually. They don't have solvable subgroups of bounded index. In fact, they're perfect. They're simple modular center, so there's nothing. Yeah, not virtually solvable. And now we're going to gently push gamma bar into a rational. I want to replace C with the rationals, because I want to start to use arithmetic. I want a Q-defined group, and I want the integers inside.
Didn't we have to do this finite index subgroup somewhere in the group of 2?
Yes.
And so we also have to go to a finite index thing.
Well, it doesn't matter, because you can increase the degree sufficiently much to at this point, being linear is you can just induce up to, you can just by paying the price of increasing this n. So, but very quickly we have to start to take finite index subgroups anyway. So, yeah, right. So, well, let's play the same game. This is now finitely generated. This gamma bar is a quotient. It's not a closure. Sorry, this is confusing notation. So this is just a quotient. So it's finitely generated. So again, gamma bar lives inside. So I can now replace. Right. So gamma is a finitely generated. So lives inside GL and let's call it again R, finitely generated ring, subring of C. And from the very beginning, I want to throw Q to it, so I can assume that this is finitely generated Q algebra. Q subalgebra. Yeah? So just want to throw the rationals at it, so that I have no problems with finite images anymore. Now, okay, again, now what we have, this is again Noetherian, non-zero divisors, the Jacobson radical of R is 0. And so the intersection of the maximal ideals is trivial, and the claim is that exists one maximal ideal of R such that the image of gamma in when you reduce in GLN R mod M is still not virtually solvable. Okay. Now, why is that? Well, this is because of a strengthening of the Lee-Cauchy theorem that I mentioned last time. So last time we proved that if a group is solvable, if a linear group is solvable, then actually it is virtually triangulizable. Yeah, but actually you can also control the index. So here is a statement of a stronger result due to Platonov in characteristic 0. So let gamma be a subgroup of GL and well, characteristic 0 make it C, right? Yeah. And now I'm a bit confused if I remember this correctly.
You cannot control the index of the triangulizable group, but the index of the solvable.
No, the index of the triangulizable group also can be controlled, but maybe not over C. Maybe for given. Yeah, I think this is correct. So in characteristic 0, assume B virtually solvable. Then exists some f of n integer such that gamma has a subgroup of index at most f of n. Index at most f of n, which is triangulizable. Okay, so it's
you just have a group of rotation in SO2, just a cyclic group of very large order. So it's abelian already, but
it's all C, all an algebraic closed field. It's a theorem. it's a difficult. I mean, okay, it's much more involved than the Lee-Cauchy theorem. Yeah. Right. So what is the well? If this was not true, then all the images of gamma here will be solvable by a bounded finite bit. Yeah. But now gamma is finitely generated. So inside gamma, I will take the intersection of all subgroups. I can take delta, the intersection of all subgroups, normal subgroups of gamma, of index of the such that the index is at most f of this. Oh, no, I shouldn't call it n now because I still have two n's. Yeah, u. This is more than f of n. Now delta itself is a finite index in gamma because gamma is finitely generated, has only finitely many subgroups of bounded index. But now the image of delta in each of these guys is triangulizable, so it's solvable of bounded length. Yeah. So I will deduce somehow that this will deduce, so this will give me that delta is solvable.
What are you assuming
if claim is wrong. If the claim is wrong, then this is virtually solvable. The image of gamma is virtually solvable. So if I take the intersection of all subgroups of index which are bounded by this result here, the image of delta in each of these groups will be solvable, and in fact triangulizable. So it will be solvable of solvability of length at most n. But if the group is residually solvable of length at most n, then it is solvable of length at most n. So I would deduce that delta is solvable, and then gamma will become virtually solvable, which is not possible. Yeah. Okay. So claim is true, but then I can just replace. So now replace gamma with its image in GL and R mod M. And basically we reduce into the case when gamma lives inside GL N. And now this thing is a number field. Yeah, remember, this is now again the Neustadt, and that's this is a field which is finitely generated as an algebra over Q, so it must be a finite extension of Q. Yeah, so L. But actually, I can just put this inside GL even bigger integer, n prime over Q. Right. I really don't care so much that it's a number field.
You know that it's algebraic?
It's finite extension. What? The degree is finite. The Neustadt, yeah, it's a cheap result. It's you cannot have infinite extensions which still remain finitely generated. At some stage, this all boils to the fact that if I take a transcendental extension of a field, there are infinitely many primes here that I have to invert infinitely many different irreducible polynomials, so I cannot generate it as an algebra. Yeah. Right. Okay. And so now we are reduced to the case when gamma is not virtually solvable. And now it's a finitely generated subgroup of some linear group over Q. And where is the time? Right. Still have a little time to finish the. Now we're going to, of course, now we're in good shape. We're going to take the Zariski closure. So now let G be the Zariski closure of gamma in GL Q. Now this group is not solvable. So G. Okay, so then I can take the connected component. The connected component is a finite index subgroup. So I can just intersect it with gamma, and by passing to a finite index subgroup, which I'm allowed, passing to this, assume that G is connected. Right? We started to take finite index subgroups now. Now it's connected, not solvable, but then it has a simple Q-defined factor, right? So in this case, the radical of G is not equal to G. So G has a semi-simple Q-defined quotient, but then take a factorization of this semi-simple quotient as a product of Q-simple groups. So basically, G maps onto Q-simple group G1, right? And the map is Q-defined. But then the image of the image of gamma here, which is Zariski dense here, it will be Zariski dense here. Yeah, so there. Yeah, so I can just replace and because it's Zariski dense, we only care about Zariski dense now. It's not going to be virtually solvable because this is now Q simple. So again, by passing to this quotient, can assume pass to G1 and assume now that G is Q simple. Right, without loss of generality, we assume that G is Q simple. And the next final step at this moment, for the moment, it's not, is that we want G to be simply connected because now there's the simply connected version of G. And this is an isogeny. Yeah, of the simply connected version of G onto G. So I define this for absolutely simple groups, but the same proof works for Q simple groups. Yeah, there's still an isogeny, and we have that the image of f of the rational points here is coabelian. Okay, so GQ modulo this is abelian of finite exponent. Okay, but then I just intersect my gamma with the image, right? And now, therefore, this has finite index in gamma. Right? Because gamma modulo it sits inside here, so this is an abelian group of finite exponent, and gamma is finitely generated. So there's so this is the quotient is finite, right? But then I just pull it back and define my new G, gamma tilde, is the one where I take the pre-image of this intersection. Right? Now this lives inside G tilde Q.
An extension of gamma.
Yeah, it's a finite central extension of gamma. Yeah, and yes. So this is a finite central extension of gamma, but now this is still a linear group, and now gamma tilde is residually finite. So I can pass to a finite index subgroup where this is really isomorphic. So pass to a finite index subgroup. Subgroup gamma tilde 0, which intersects trivially the kernel of f. Yeah, kernel of f is some finite subgroup. You can always omit it. So we have now gamma 0 tilde intersecting the kernel of f trivially. But then this means that gamma tilde 0 is isomorphic to a finite index subgroup of my original gamma, right? Because now it's an injection, yeah. And I really want to know about the finite images of this guy, so I can just as well know about the finite images of that guy. So by this reduction, so by replace G by G tilde and gamma by this guy, basically assume that G is simply connected. Okay. So this will be this G here. Yeah, that's the G that occurs. And it's important it's simply connected because otherwise there's some problems. We're going to see that if G is simply connected, then the congruence quotients of these groups are very nice. They're kind of, on top you have simple groups and then you have P groups. If G is not simply connected, then you can have a billion, just in the same way that here, you can have a billion quotients, infinitely many a billion quotients here, and things get bad. Okay, so in my next talk, I'll start to continue the proof of this, and now I'm going to study the congruence completion of these groups. Thank you.
But the price is bounded, right? If you don't simply connect it, then it's not. You won't get arbitrarily larger billion, right?
Yeah, because it's finitely generated. Essentially, you're kind of going to run this argument. Yeah.
So it can.
Can we assume that we map onto SLN FPR, right? Just any. I mean, because it was specifically SLN didn't matter, right?
Yeah. Here, this could have been any subgroup of them. The only thing you don't want that something that is boundedly solvable by extended by a bounded group. Yeah, you want to eliminate
simple groups of.
Yeah. You can take simple subgroups. Yeah, simple groups of finite ranks. I just gave this as a concrete example.
How about alternating?
Or alternating, it's not true. Because of this result that here I said instead of these you can take alternating groups of increasing rank, and then you can get only them as finite images. Yes.